Gravity is a force we encounter constantly, though it often goes unnoticed in our busy lives. It acts as an invisible pull between objects that have mass, drawing them toward one another without any physical connection. This pull operates everywhere, from the smallest particles to the largest stars. Picture yourself standing in a room and holding a book at arm's length. When you open your hand and release the book, it falls directly to the floor. The reason lies in the attraction between the book and the Earth. The Earth possesses vastly more mass, so its gravitational pull overcomes the book's smaller influence and brings the object downward. In simple terms, gravity means that any two objects with mass will pull on each other. The greater the mass, the stronger the resulting force becomes. A dropped book demonstrates this clearly because we can watch the motion happen right before our eyes. The book accelerates toward the ground at a steady rate due to this pull. Air resistance plays only a minor role here, allowing the effect to remain easy to observe. Meanwhile, the book exerts an equal but opposite pull on the Earth, yet the planet's immense size prevents any visible movement in return. That mutual attraction is the heart of the matter. Repeating the drop with different books shows the same result every time. The speed of the fall depends mainly on the Earth's pull rather than the book's own weight. The concept stays the same, no matter which object we choose to release. Gravity remains constant in its behavior during these simple tests. Now, let us recap the idea in plain words. Gravity is the invisible pull between objects. Releasing a book lets us see that pull in action as the object drops. Nothing more complicated enters the picture at this stage. This understanding forms the foundation for everything that follows. Everyday observations like falling objects reveal the presence of gravity without requiring special tools or advanced knowledge. The same force operates whether we stand on the ground or float in space, though its apparent strength can change with distance and mass. When the book hits the floor, it stops because the ground pushes back with an equal force. Yet the gravitational pull itself never disappears. It continues to act on the book even after it lands, pressing it gently against the surface. In plain words, once more, gravity pulls things together. The dropped book example shows this pull at work in the most direct way possible. Now that we understand how the book remains drawn to the floor long after it lands, we can watch gravity act through two simple tests anyone can try at home. Begin with the drop test. Choose two objects that differ clearly in weight, such as a heavy shoe and a lighter tennis ball. Stand on a chair or step stool, hold both items at the same height, and release them together. You will see them strike the ground at almost the same moment. Gravity gives every object the same downward acceleration when air resistance stays small, so extra mass does not make one fall faster than the other. To put it plainly, the pull acts equally on light things and heavy things alike once we remove the slowing effect of air. Next comes the ramp test. Place a flat board or a sturdy book on the edge of a table so one end rests higher than the other, forming a gentle slope. Set a small ball at the top and let it roll. Notice how steadily it moves downward. Now raise the starting end to make the slope steeper and roll the ball again. The steeper angle speeds the ball because gravity pulls it more directly along the surface rather than partly against the ramp itself. In everyday words, a sharper tilt gives gravity a straighter path to speed the ball forward. These two tests together confirm the same basic rule we met with the falling book. Gravity draws objects toward one another at a steady strength set by mass and distance, whether the motion is straight down or along a slanted surface. Each time you repeat the drops or change the ramp angle, the outcome stays the same because the underlying pull never changes. That steady pull we just measured with the book and the ramp is exactly what holds you in place on the floor right now. Earth is a giant ball of rock and metal, so its mass creates a strong downward tug on everything nearby. When you stand still, your feet press against the ground because gravity is drawing your body toward the planet's center at a constant rate. Jump up for a moment and you feel the same tug bring you back down. There is no extra force at work, only the one we timed earlier. The same rule reaches far beyond our feet. The moon is held in its path around Earth by this identical pull. Earth's mass tugs the moon toward us, yet the moon moves sideways fast enough that it keeps missing the surface and simply circles instead. If the moon slowed down, it would fall straight in. If it sped up, it would fly away. The balance between speed and pull keeps the orbit steady, just as the ramp angle balanced the ball's roll. Let us pause and restate each case in plain words. With the falling book, mass and distance set the speed of the drop. On the ramp, the same mass and distance set the steady acceleration down the slope. Standing on the ground, that same strength keeps your body pressed to the surface. For the moon, the strength is smaller because the distance is greater, yet the rule never changes. Every object pulls every other object toward itself. This single force explains why leaves settle to the earth, why rivers run downhill, and why the moon stays overhead night after night. Understanding it lets us predict how things will move without guessing or hoping. Once we see the pattern in these everyday motions, the wider universe begins to make sense on the same simple terms.